Hello, my name is Brian Crafton, and I will be presenting our work titled Statistical Optimization of Compute Memory Performance Under Device Variation. My co-authors are Samuel Spetalnick, Jong-Hyeok Yoon, and Arijit Raychowdhury, and we are from the Georgia Institute of Technology and the Gyeongbuk Institute of Science and Technology. Compute memory is an exciting technique that can greatly increase memory bandwidth and perform multiplication and accumulation on the bit lines of a memory array. We can illustrate this by comparing a compute memory array and a typical memory array. First, we swap our sense amplifiers for analog to digital converters, and now we can enable multiple word lines at the same time, and add the results on the same bit lines. This additional functionality makes compute memory an excellent kernel for matrix multiplication, which serves as the basis for deep learning applications. In this work, we consider a 128 by 128 RM macro, but the technique applies to any memory. We assume binary weighted cells and 8-bit weights and 8-bit inputs. For 8-bit weights, we use 8 adjacent cells. Every 8 columns or bit line shares an ADC, for which we use either a 3-bit flash or 6-bit SAR, which is based on area constraint in the RM macro. 8-bit vector matrix multiplication, or VMM, is implemented by shifting and scaling the compute memory result of each input bit and each weight bit. And so if we have 8 input bits and 8 weight bits, we'll have 64 binary vector matrix multiplications that we will add together to create an 8-bit VMM. I am showing this idea with the animation in the bottom right, where we process a single binary VMM at a time. In this example, we only read 2 word lines at a time for simplicity, but note how we can operate faster than 2 word lines at a time because we skip the zeros. All memories used to perform compute memory suffer from device variation. In this work, we focus our attention on resistive RAM, and to gather realistic data about device variation, we collected 8,000 measurements on a 40 nanometer foundry RM array that our co-author, Jong-Hyeok, recently presented in ISSCC 2021. First, we show the resistance distributions of the set operation for the low resistance state and reset operation for high resistance state. We collect data for 3 different write voltages and show the distributions as cumulative distribution functions. From this data, we can infer the mean and standard deviation of the resistance values, and we observe that by increasing write voltages, we can reduce the standard deviation as a percentage of mean and thus improve compute memory accuracy. To evaluate the impact of these device variations, we can perform 8-row parallel read after writing the cells with a random uniform distribution. The result of this is presented on the right as a confusion matrix showing the actual ADC output versus what we expect to receive based on the weight encoding. We show the results of this for 2 different write voltages. From these results, we should conclude 2 things. Device variation can be lowered with increased write voltage, and compute memory error rate increases with device variation. Lastly, we use these ideas and the data we have collected as the design space for practical experiments in all our simulations in this work. So now that we understand that device variation leads to computational error in compute memory, we ask ourselves, how do we quantify this error and how does it translate to application performance? To quantify error, we use mean absolute error, which is the absolute difference between the result of noisy compute memory and correct matrix multiplication. And to translate mean absolute error to application performance, we inject error into a CIFAR-10 simulation and sweep both LRS variation and the number of parallel word lines read by our ADCs. For this example, we try 1, 4, and 8 parallel word lines and sweep between 0 and 20% LRS variation. We find that either increasing LRS variation or the number of parallel word lines results in increased mean absolute error and decreased classification accuracy. So if we know how variation impacts computational error and application accuracy, and we cannot reduce device variation because of physical limitations, then we should reduce the number of word lines we read in parallel, but this will unfortunately compromise performance since we read fewer word lines in parallel. But can we do better than this? And the answer is yes. As we saw earlier, 8-bit matrix multiplication is implemented as 64 independent binary vector matrix multiplications, or binary VMMs. Each binary VMM is followed by shift and add logic to multiply each result by the corresponding magnitude. So this means that computational errors that occur in binary VMMs with a large corresponding magnitude will be far more detrimental to our result. For example, the binary VMM between the least significant bits is scaled by 1 because 2 to the 0 is 1, and the binary VMM between the most significant bits is scaled by 16,384, or 2 to the 14. Hence, errors that occur for the most significant bits are exponentially more destructive to the result. So, to quantify this idea, we extract the error contributed by each binary VMM for our CIFAR-10 simulation in the previous slide, and then plot the percentage-wise breakdown in the table shown here. we find that over 80% of the error comes from only 10 of the 64 binary VMMs. And so the idea is, for binary VMMs with high error, we should read slowly, and for binary VMMs with low error, we should read fast. So our optimization objectives choose some number of word lines to operate each of the 64 binary VMMs at, such that we maximize overall performance and satisfy our error constraint. To approximate expected error and performance, we build error models discussed in detail in the paper. Next, we compute the expected error and performance for all possible operation speeds for each binary VMM and construct a table. So if we have 64 binary VMMs and we want to consider operating each one between 1 and 16 word lines per cycle, then our table will have 16 times 64 or 1024 entries. So the solution to our optimization problem is minimizing the sum of cycles across a 64 binary VMM, but ensuring that the sum of error across a 64 binary VMM does not exceed our threshold. This optimization problem can be classified as multi-class knapsack with a minimization objective because we want to minimize total cycles. We implement this problem using an ILP solver in Python with the constraint shown here, and it runs in only 10 milliseconds. So an example of what we might look to do is operate the first binary VMM at 16 word lines per cycle since the error is so low, while also choosing to operate the last binary VMM at 1 word line per cycle since the error is so high. So now we have made it through the algorithm and we'll see some results. Because of the short presentation, we will focus on only a few results and direct listeners to the paper and GitHub for specific details. The first research highlight is that we can obtain tight control over the error and thus accuracy of the network. In the top right figure, we simulate 3 designs. The first design is a baseline design without any optimization. And the second and third designs use the proposed optimization algorithm with error constraints of 0.25 and 0.1 mean absolute error. These error constraints are chosen because for ResNet 18, they translate to 1% and 0.25% accuracy degradation on ImageNet. In each case, we simulate with 12% LRS variation and 40% HRS variation. Then we plot the mean absolute error for the first 8 layers of ResNet 18 on ImageNet. We observe that our algorithm maintains tight control over the error constraints, while the baseline design does not. The next research highlight is performance optimization while satisfying our error constraints. We sweep from 1% to 20% LRS variation and fix HRS variation at 40%. Next, we observe the classification accuracy on ImageNet and performance of each design. In the bottom left figure, we show classification accuracy for the 3 designs. For the baseline design, we begin to see accuracy fall off at around 8% LRS variation. Meanwhile, our optimized design maintains constant accuracy despite increasing LRS variation. We do this by reducing performance, which is seen in the performance plot on the right-hand side. However, at low LRS variation, we find that the optimized designs can obtain a significant performance improvement, between 21% and 44%, depending on choice of ADC. That's all for my presentation, and thank you for listening.